Kia ora. I'm just going to do a bit of a walkthrough pretty much of some of these questions on page 69. Okay. Alison throws a stone vertically into the air. The relationship between the height of the stone in meters and the time in seconds since she threw it is given by h equals 2 plus 20t minus 5t squared. So the first thing I like to do is look at what the picture is going to look like. So what's the highest power? 20t negative 5t squared. So it's a negative parabola. So our model is going to look like this. So I just like to have an idea of what I'm looking at. How far above the ground was the stone when it left her hand? How far above the ground was the stone? So the relationship of the height of the stone and the time is given by that. So I guess it leaves her hand at t equals 0. That's when we start measuring, right? Okay, let's have a look at that. So h, so that's just a substitution problem first, equals 2 plus 20 times 0 minus 5 0 squared. These two things are going to come out at 0, so it's just going to be 2. So see how we had h? I would actually like to call it h in regard to 0. So h when t is 0. So it'd probably be cooler to have h of t, height in regard to time, right? So then it makes it obvious that, yeah, we're looking at time 0, and then that substitution gives us 2. Now we're going to have to do units. H is in meters, so we're going to have to put 2 meters. How do they spell it? RS. Okay. How far did the stone travel during the first second of its flight? How far? This is talking about height. And how far did it travel during the first second of its flight? So we know it starts at 2 meters. So at its first second, that's the height when t is 1, right? So it's going to be 2 plus 20 times 1 minus 5 times 1 all squared. So it's going to be 22 minus 5. Whoa, what the heck? Man, she's got a ridiculous arm on her. Are you flipping kidding me, Alison? Alison got the stone 17 meters in the air. This girl is a beast. I have to see it for myself. Let's look at this model. Yeah, this is incredible. Is this like a world record attempt or something? Plus 20x minus 5x squared. What the heck, Alice? Man alive! Is that 17 meters? I want to go outside and throw a stone up in the air. Okay, anyway, it looks legit. Yeah, so we can see that after 1 second, here's the stone, 17 meters in the air. Crazy. Oh, shot, Alison. Okay. Yeah, so how far did the stone travel during the first second of its flight? So we're actually looking from where it started up to that point. So the height's not just 17, because we know that the height at 1 second was 17, but we also know that the height at 0 seconds was 2. Right? So we're not quite done. I'm going to say it's going to be 17 minus 2 equals 15 meters. Right? So that's this from here to here. And then that there is the first second. 1 second, and then it flew up 15 meters. Okay, let's keep going. How fast? Ooh, not how far, because how far is all about s of t, which is displacement, right? Whereas how fast is measured by velocity. So we're looking at v of t at this point. So how fast was the stone traveling after 1 second? So how do we get from s of t to v, s of t to v of t? This is going to be differentiation. I'm going to write I'm just going to go d by dt. That just means differentiation in regard to t. Alright, so to get from that to that, we're going to have to differentiate. So we're going to have to take our height equation and differentiate it. So we're going to have to go h dash of t. And then let's get our original function. 2 disappears, becomes a 0, plus, differentiation, it's been a while since we've done it. 20, we take 1 from the power, then, we divide by the power, then take 1 from the power, plus 20 minus 10t. Okay, and then I'm going to get rid of this, I can't bother writing it out again. Okay, so how fast after 1 second? So we're going to have to do h dash of 1. So h dash, we decided that the derivative of height is going to get us from, so height is a measure of displacement, so the derivative is going to take us to velocity. So h dash of t is a measure of how fast. How fast equals that, right? Whereas this one was height, right? And now we've gone down to a how fast, and that is by the derivative. So h dash of 1 is going to be 20 minus 10 times 1 equals 10, and so it's meters and seconds, so it's going to be 10 meters per second. And that, oh man, slash fraction, ugly, but it looks kind of cool here, so I'm going to stick with it. Right, I'm hoping getting these right, because I'm probably explaining them to a class, right? Let's have a look. So I would say this is a good way to do it anyway, to do a few questions and then check that you're not way off. 2 meters above the ground, oh shucks, I missed a detail. 15 meters, yes, 10 meters per second, phew. Okay, we're on the right track. Okay, calculate the stone's acceleration after 1 second. The stone's acceleration after 1 second. So we went from displacement down to velocity, and velocity to acceleration takes another differentiation from velocity. So we're going to have to do, I'm going to call it h dash dash of t. And so we've gone from height down to how fast, and now we're going down to acceleration. And that's going to be the derivative of the derivative, or the double derivative. Right, so we're going to get that, and it's going to become, that 20 is going to disappear, and then it's just going to be negative 10. Oh, look at that, we don't even need to substitute it, because h double dash of anything is going to get us negative 10. But let's just do it anyway. H double dash, and they want to know after 1 second, equals negative 10. Wow, that was tough. How do we measure that? It's acceleration's a weird one. It's meters per second, because meters per second is our velocity, right? But acceleration is meters per second, right? It's meters per second squared. And that's a physics thing for you. It does make a lot of sense with notation, because we're doing it in regard to time. So of course every time we lay it down, it's just going to add on another per second, and then it does another per second. So that's why it becomes per second squared mathematically. Right? Okay. Anyway, the acceleration of the stone the whole time. Let's have a look at this. So what we're going to do is we're going to call this f of x, and let's just have a look at the derivatives. So we can sort of start seeing these relationships visually, because I kind of like to see things visually. I'm a visual learner. So see how our velocity, which is our derivative, our velocity of the stone, so the stone when it leaves her hand is at its maximum speed. That initial throw is like, boom! She threw the stone at the air with a superhuman throw, and then the velocity of the stone just continues to decrease. The stone is at maximum speed the moment it leaves her hand. Then things like air resistance and gravity start contending and slowing the stone down. And its velocity decreases until it hits 0, but then the stone actually, the displacement, you can see the stone comes closer and closer, and I think at this moment here it may hit her on the head if she threw it perfectly vertical, but it doesn't seem to. It seems to fall into the earth forever, and it falls into the earth and then eventually hits the earth's core as it goes down and down. But yeah, let's have a look at acceleration. F double dash of x. Now, acceleration is constant. Be there, I want you to be there. Dang it. y equals 10. Fine. Oh, whoopsies, my bad. Negative 10. Alright, and I'm going to make these dashy for you so you can see what's happening. Right. The next derivative, acceleration, the deceleration is constant. It's constantly decelerating at 10 meters per second. Alright, it's constantly decelerating. Every second that goes by, its velocity decreases by 10 meters a second. Okay, so yeah, maybe I over-explain that. I definitely over-explain that, but okay, anyway, calculate the stone's maximum height. Now, we're going to have to go back. We could look at Desmos and totally cheat for that, but nah. Max, we know it's a negative parabola from the initial formula. Height is a negative parabola. So the max is obviously going to be here. How do we find a maximum point? We're going to have to go back to our calculus. Remember, when we differentiate, zoop, zoop, a negative parabola is going to get us to a negative linear graph, and this max will correspond to the point where the velocity of the stone peaks out. I mean, when the velocity of the stone hits 0, should I say, not peaks out, when the height peaks out. When the velocity reaches 0 is the point where the stone turns around and starts falling into the core of the earth. Okay? So, we're going to have to use our h dash of t, and we want to know when h dash of t is 0. So, we're going to have to go back to here. So, we know that h dash of t is 20 minus 10t. 20 minus 10t equals 0. 20 equals 10t. T equals 2. Beautiful. At 2 seconds is when this happens, so that corresponds to when the max height of the stone occurs. Maybe this situation is more realistic than I'm giving it credit. Okay, t equals 2 seconds. Okay, one more question. When was the velocity of the stone equal to 12 meters per second? Okay, velocity, so h dash of t being equal to 12. So we're just pretty much doing exactly what we did over here. I want to try and fit it on the screen for you. 20 minus 10t equals 12. Let's do some rearrange. 8 equals 10t. T equals 8 over 10. 0.8 equals t. Wonderful. When was the velocity of the stone equal to 12 meters per second? I feel like I rushed there and made a blooming mistake slashing off the screen. Get that over there. Getting that over there, so we're minusing 12. 8 over 10. Yeah, it makes sense. So at, I like using these symbols. Most other teachers don't really do it. At 0.8 seconds, the velocity of the stone is equal to that. Sick. That's page 69, baby.